So last week's video should be online. Again, as a reminder to everybody, watch my previous lectures that you can find on my website. We're not going to cover all the material in class. It's all there for you guys to watch. There's no point in me just rehashing things that I've said previously. I want to open this up to more focus on skill set development, problem set development. I've had somebody come up here and ask me about a couple synthesis problems, so we can begin to discuss synthesis a little bit today. But I want to, before we get started, I want to make one sort of, I guess, announcement, and that is that you guys are hopefully all aware that next week is going to be our first quiz. And the other thing that I said last week is I sort of reiterated the point that this course is cumulative, not necessarily even from just within the chapter, but from all the chemistry courses that you've ever taken. Now, not to scare you in that extent, but certainly as we discuss things like synthesis, right, it's going to be implied that you know reactions that you learned last semester. So with the upcoming quiz, I'm going to try to give you guys a little bit of, I'm not always going to do this, but this is the first quiz, and I want to make sure that I get you guys on the right path to make sure that you're successful in the course. So I'm going to tell you what's going to be on the quiz, not the specific problems, but at least give you specifics in terms of what to study. You will each have, so in terms of the material from last semester, if you want to focus in on things, okay, first warning to everybody, don't let that happen again. But the chapters that you should be focusing on, again, I hope that you guys can all draw. As I said previously, I don't care that you can tell me whether a compound is R or S per se. I mean, you should be able to do that, but it's more about the ability, for example, to redraw molecules in different orientations, which is going to be important when you're talking about mechanisms and certainly synthesis. If you can't draw the molecules accurately, then you're setting yourself up for a difficult time in that event. But specifically, your focus should be on, I would say, chapters, say, for example, 6 through 9. That is going to encompass substitution, elimination. Again, I hope that you can all do acid-base chemistry, Lewis acid, Lewis base, Bronsted acid, Bronsted base. As well as alkene chemistry and alkyne chemistry, in addition to, which I'll get to in a second, a little bit of radical chemistry as well. So we didn't really discuss radicals yesterday. They represent a sort of just a different class of bond reorganization, right? Where instead of doing heterolytically 2 electrons at a time, you're moving them 1 at a time. They will come up in about maybe 10% of the reactions, so it's not something that, it's something you should know, but in terms of the priority, you've got to make sure that you can do homolytic bond formation first. As I'll get to, the same can be said about oxidation or transition metal. Specifically, for the most part, when we're referring to transition metal chemistry, we're really referring to oxidation chemistry. So you're going to basically get 4 questions. Okay, 2 of them are going to be on sort of organic 1, so chapters 6 through 9. You're going to get 1 question that's simply going to ask you, here's a reaction, what's the product based upon chemistry that you learned last semester. You will also get 1 that involves a mechanism from organic chemistry 1 that's going to ask you, it's going to show you the full reaction, and you're going to be asked to tell us what the mechanism is. And then you're going to get the same 2 types of questions for chapter 10, for the alcohol chemistry, okay? So that gives you some focus. This is what I want you guys primarily focused on right now, is learning the reactions, and perhaps even more importantly, as hopefully I made clear last class, mechanisms. Because if you understand mechanisms, you should be able to teach yourself a lot of the chemistry that we're going to learn today. I want to make one sort of point, and again, you can go back and read a little bit about these, and then we'll get to some other chemistry. But again, rehash on radicals a little bit. We're not going to be discussing radicals for a little bit, but what we are going to start to get to that I thought might be worth just spending a little bit of time mentioning before I turn specifically to answering some of your questions and perhaps doing some problem solving, is we're going to start getting to a little bit of oxidation and reduction chemistry as well. And oftentimes these reactions will involve perhaps mechanisms that we're uncertain of. And so oftentimes in the past I've sort of glossed over chemical reactions, but one example that you saw last semester, for example, is if you take oxygen, right, we'll just focus on the first step here, and you treat it with osmium tetroxide. Do you guys remember this reaction? Right, so if you take an alkene, right, and you treat it with osmium tetroxide, there's a workup afterwards. It's a reductive workup, but at least in the first reaction, in this first step of the reaction, what is the product that forms? Syndiol. So right, so you'll get a syndiol ultimately, right, after the reduction, but the first step of the reaction, well, yes, you get a syndiol following an intermediate that we'll get to, which is, I guess we'll just say NaHSO3, which is the workup that you do. But the reason I want to focus on this is a reaction that does involve transition metal chemistry, and it's not even necessarily that we're talking about transition metal chemistry here. What we're talking about is specific molecules that will behave a little bit differently than we're used to with standard carbon. So I just want to make a few points. We're not going to, if you want to learn more about this, you can certainly take an organometallic course. But the intermediate involves a sort of concerted process, right, whereby you generate this cyclic osmium species. Okay, and what sort of drives a lot of these reactions is that the sort of, in this case, osmium is at a very high oxidation state, and so it sort of performs this process. So you may have seen in the notebook sort of Roman numerals, right? If you guys remember this, you'll see some Roman numerals assigned to these metals, and in this case, the osmium, does anybody remember what that is? We're really going back here, checking your memory. Well, it's 8. Okay, and so is that right? But the way that you think about sort of the oxidation, right, is that you think about the number of, in essence, I guess you could think about them as covalent bonds, if you will. But the number of bonds that you have in this system, right, is 8, right? And through this process, you're actually dumping a couple of those electrons into the osmium, and then you're getting to osmium-6. Okay, and then you end up doing the workup, which reduces this off, and we won't get into that much. But this is perhaps one of the few examples that you guys saw last semester, and sort of referred to as an oxidation in many ways. And what I wanted to mention very quickly is that I think it helps sort of clarify things that can sometimes be confusing. We hear the term oxidation, and especially for the most part, I think what people get most comfortable with oxidation, we're about to see now. It's oxidizing alcohols up to aldehydes, ketones, and ultimately carboxylic acids, which hopefully you guys have seen, and then sort of the reverse reaction of a reduction. But at the sort of core of this, I mean, where did you guys first hear about oxidation and reduction? When did you first learn about these terms, oxidation and reduction? In Gen Chem, right? And what do these terms at their core mean? What does the oxidation mean? What does the reduction mean? Yeah. Yeah, well, it's about the change in overall electrons, right? And so, do you guys remember the term oil rig, right? Oxidation is loss. Right? Reduction is gain. Right? So oxidation is loss, reduction is gain. And so when we start to think about some of the chemistry that we're going to be getting to, say for example, carboxylic acids from alcohols, which is one of the things that we're going to get to fairly quickly, right? When we take this reaction and we convert it into, say, an aldehyde, right? Who can tell me what the reagent is for this? Somebody that's hopefully at this point. Come on. What's the reagent for this oxidation? Yep.
PCC.
It's PCC is how you stop it at the aldehyde, right? So read up on that. So this is an oxidation. It's a chromate reagent that's in a higher oxidation state. At the end of the day, it's taking on a couple electrons through this process, which you can go and certainly read about. But the point that I want to make here is what's the sort of, if you, absent from the actual mechanism, let's just sort of balance the equation here, right? Forgetting what the actual reagent is that does this, because I just wanted to discuss why we might consider this an oxidation or a reduction. How do we balance this equation? What would be needed to balance this? This is a balanced equation. Conservation of mass. Right? How are we going to balance this equation? I'm not talking about actually running the chemistry, I'm just talking about generically what's the difference mass-wise in terms of what's on the left and what's on the right. Irina. Well, right, so how many carbons are in this? If we assume R's are the same. Right, there's basically the one carbon here. There's one oxygen. Right, this has 3 hydrogens. This has 1. Right, so the balanced equation basically tells us that the difference here is hydrogen. Right, and so this is an oxygen. So what's happening in this process? We're losing 2 electrons, right, from this. Where are they going, at least in terms of the balanced equation? Right, over with the hydrogen. So this is, again, it's, as you know, you're not generating hydrogen in this reaction, and hopefully I'm making that abundantly clear that I'm not telling you guys that that's what's happening in this reaction. What I'm sort of trying to explain to you guys is why this would be called an oxidation. Now let's think about the next step, right, because it's a little bit more complicated. When we now take, say for example, an aldehyde, and we oxidize it up to a carboxylic acid, and I think this is sometimes where some of the confusion could come around, especially since the term oxidation sounds so much like oxygen, right? And so you're sort of assuming that maybe you're adding oxygen to the system and that's what it is. But no, I'm trying to make the point that it's about oxidation here. But this, in a way, it's a little bit different, right? We are, to sort of balance this equation, you would need what? Molecular oxygen. We would just need oxygen, right? And we're not going to have that, right? So, oh, sorry, wrong side. Right, so we'd have to have oxygen to this side, right? But in reality, what's happening here, right, is that to, in essence, really balance this equation, you can't have this, but what do we have in this oxidation is water, right? This is one of the differences, hopefully you guys will see, between PCC, right, and chromic acid-based oxidations. Chromic acid-based oxidations are run in aqueous solutions, so the intermediate that you're getting to is that hydrate, right? This is the sort of subsequent oxidation. And then what ends up happening there now is we lose those 2 electrons from the hydrogen, right? So really, if we want to balance this equation right, we can basically say H2O, right, plus the aldehyde, right, leads to water and sort of hydrogen, right? So overall, really what's happening is this water, I guess you can think about it this way, again, just to sort of make sense of this, that in the same instance, you're in essence losing hydrogen also from this system. So you're losing 2 hydrogens from the system. But in reality, it's because the intermediate, you can sort of think about it's really the intermediate that's being oxidized, right? So the intermediate which comes through water, right, and the aldehyde. So does that make sense? So again, this is just something that I remembered when it became a little bit clear to me. It started making sense in terms of oxidation and reduction. And so that way, once you start seeing, for example, metals that begin to change their oxidation state, and they begin to become reduced throughout the process, then they're sort of transferring those electrons over to the system in a different way. And again, it's not to say that you're generating hydrogen in these instances, but it's just to sort of balance the equation to see why this would be considered an oxidation. But again, back to what we're discussing here, right? This idea of going from, say, 8 to 6. And so when we think about, again, the oxidation of, say, chromic acid or PCC or one of these reagents, right? What we're doing here is we are sort of oxidizing, so in the case of chromium, right, the chromic acid, right, or the sort of Jones reagent, as we call it, sort of sulfuric acid and chromate, the real oxidant in this case is chromic acid. You'll sometimes also see CrO3 plus sulfuric acid in water. You can easily draw a mechanism showing how CrO3 hopefully can go to chromic acid. But usually when we think about the mechanism, we think about it from this. So again, this is going to be an oxidation, same way that this was, which means that the reagent is going to be reduced, which means that the sort of electron count that we give it, right, is going to sort of drop. Okay, and so in this case, based upon kind of how you would count those, and not to get into electron counting per se, because there's changes once you get to different types of bonds, like, again, that's for another day, but just sort of counting the amount of electrons in terms of the covalent bonds, if you will, around this system, right? In this case, there are what? 6, right? So we'll assign this an oxidation state of 6, and what happens in this mechanism is we're going to take that oxidation state of 6 and we're going to convert it into 4. Okay, so the first step of this reaction, right, is going to be, and I guess this will be the first mechanism question of the day, that I hope that you can all figure out, is how will this and this react to give this? And ultimately, at the same time, what is the sort of the byproduct of this, and how would you balance this equation? What type of reaction is this? Right, so if we wanted to do this reaction, at least in terms of pushing the electrons, this is going to be in an aqueous solution. How might we push the electrons to get to that intermediate? Yeah? Say it again. The lone pair is on the oxygen. So what we can do is, that's one possibility, right? So there's a couple ways that we could draw this, but I like that. Hold on, let me just... Okay, so then, go ahead. These or these? Okay, so let me ask you a question. Why... There's some good intuition here to go there. We haven't really discussed carbonyl chemistry yet, but maybe you can tell everybody why you decided that you wanted to push the electrons from the chromium up onto that oxygen. Well, certainly it could come back down, but a more direct way would have been simply moving the OH minus, right? Well, we don't generally like to have OH minus leave. This isn't a solution of sulfuric acid, so perhaps it could leave as water in some extent. But you know, there's an intuition there that I think you sort of demonstrated that I'd like to maybe get some reason behind why you thought that. Does anybody else sort of, there's two options here, and this kind of gets back to what we were, you can push the electrons onto there, you can push the electrons directly onto the OH, yeah. Could be. But usually, I mean, what's, you know, I guess this is one of the reasons why we think about carbonyls, right? We don't generally think, and we'll learn about carbonyl chemistry, so I'm jumping ahead a little bit here, but it's worth it because you brought this up, and so I'll take this opportunity to, I think, make a broader point here. you guys never see OH minus as a leaving group, right? It's one of these things that, I mean, there may be a mechanism at some point that you can invoke where OH minus, you should never say it never happens, but in general, it's one of the things that we try not to do is have OH be a leaving group, because oftentimes if OH can be a leaving group, that OH minus could then also be a base to generate O minus. So this is just one of these things that you see. But a carbonyl, right, we do see serve as an electrophile, pushing those electrons from the double bond oxygen up onto that oxygen. Does anybody have any reason? Yeah. So yeah, I think that's a lot to it. So can you repeat that maybe a little bit louder?
Breaking a pi bond is less energy than breaking a sigma.
Yeah, so what's more stable bond generally, a sigma bond or a pi bond? Sigma bond is more stable. So again, we're arguing homolytic bond energy here to a certain extent, but I think at least from rationalizing, in terms of rationalizing, I do think that has a lot to do. It's also a polarized bond, and there's other components to it. But I think in terms of having it make sense to you, yes, that is, whether that is exactly the reason why or not, I think that it's a perfectly reasonable way to rationalize it, especially in organic too. So you think about the pi bond being weaker, it's also polarized and all these other things. But for those reasons, that might want to break. Okay, we're going to be at an intermediate that looks something like this. Now, what is the oxidation state? I'm missing something here, right? Let's move that OH from here just over to give ourselves more space. But what's the oxidation of the chromium here? Still 6, right? It still has the 6 bonds to it. You've just exchanged, in essence, a sigma bond a single bond a single bond for pi bond in essence, right? Is what's happened here. Charges. How's my charge look here? What's that? I'm missing a positive, right? Where's the positive supposed to go? On the oxygen. Right? So again, conservation of mass, conservation of charge. The whole system is neutral. We got a negative charge counterbalanced by a positive charge. Up here, both things are sort of neutral. We haven't added any additional carbons to this, which sometimes you guys will accidentally do. So you sort of count everything up and you see that there's nothing new here. All that I've done is I've shown a bond from these lone pairs, getting back to the idea of what these mechanisms illustrate. Those lone pairs have simply made that chromium-oxygen bond. Through that process, the lone pair, which was owned completely by this oxygen, is now sharing, right? So it's going from, you can go ahead and count all the electrons, but you could also just hopefully rationally realize that you're going from owning a lone pair to sharing that lone pair, so it's losing an electron. So if it's neutral here, it's going to go to positively charged here. This oxygen is going from sharing that pi bond to now owning it, so it's taking on a negative charge. Okay, at this step, what might we want to draw here? So maybe at this point, what might we want to do? There's a couple things we can do, yeah? Say it again? OH group. So yeah, maybe balance basically balance the system here, right? So make it go back to a neutral state. So, you know, in reality, this reaction probably, again, this sort of gets into that sort of muddy waters and mechanisms where some things might not necessarily look the greatest in the world. Remember, this isn't a solution of sulfuric acid. So, you know, certainly the sulfuric acid could, you know, you might never, and probably would never generate this fully negatively charged species, right? There's probably acid in there that will help protonate this throughout the process, but we're just trying to balance the equation here. But yeah, I think what we can certainly do now in terms of at least bookkeeping is transfer that proton, because again, that oxygen doesn't necessarily want to have a positive charge on it, right? And this oxygen would like to pick up a proton, right? And that's going to make our system neutral. So I'm just going to continue over here. So now that's picked up the proton. Again, we're not going to change anything else. But we've made this overall system neutral. So again, we should still have 6 bonds here. 1, 2, 3, 4, 5, 6. I'm double checking to make sure everything looks good. We had 2 hydroxyls previously, so you double check everything to make sure you haven't changed anything. We had 2 hydroxyls there. We got 2 hydroxyls here. The O- picked up the proton, right? So that became an OH. This oxygen, which had an H on it, gave up that H to undergo that proton transfer, and then we have the carbonyl. Nothing else changed, right? Everything stayed the exact same. And again, I reiterate this because time and time again I see mechanisms that you guys draw where suddenly you've added something new out of nowhere. So it's really, really, really important that when you're redrawing these, you do take care to recognize that you're redrawing the molecule in the appropriate sort of fashion. Now, this, again, how you want to go through the mechanism from here, I think there's a few different ways, and again, I'm not going to sort of have some golden rule here in terms of how you do it, but certainly these begin to represent hydrates, right, which we'll learn about aren't that stable. Usually you like the double bond from a polarizability standpoint when you can do so. So that could break down, and you can even imagine it entropically. It's good to have 2 things rather than 1, so any way that you can rationalize that. But this will probably break down to water and the carbonyl, which, when we get to carbonyl chemistry, will hopefully make more sense, so I don't want to dwell on this too much. So we'll leave it at this for now. But the point is that through this oxidation, right, what we want to do is we're still at 6 here. 1, 2, 3, 4, 5, 6. And what we'd like to do is get to 4. So how might we do a reaction here that is very analogous to something that you learned that would allow us to basically put electrons onto this system, right? If you can imagine a series here, this reaction begins to become a lot like maybe elimination chemistry, right? Because what you'd like to have happen here, right, is you'd like to basically break a bond, right? And through that process, you can put the electrons up onto that carbonyl. Does everybody see how that's sort of happening? So it's a 2-step process just to sort of make, and in reality, you don't even necessarily need to sort of break that bond based upon, I think, your current knowledge, but it's just sort of the way that it happens. But yeah, this is like an elimination, and so the question becomes, how do you eliminate? I think the book simply shows water, for example, performing elimination. It could be driven through, for example, intermolecular processes where this carbonyl does so, but we'll just try to keep it as sort of straightforward as possible. So it's very much like an elimination. And again, if you look at the book, they might show a double bond. Eventually there, I'm just trying to make a larger point here. We're generating H3O. Right? And again, you can pick up the proton from this, but the point is that we've gone from the 6 bonds down to the 4 bonds. Okay? And so the oxidation state here at the chromium, and again, we can draw it as CrO2, and it'll actually oxidize even further. But at least just going through one mechanism, which will show you this process, we are now in an oxidation state of 4. And so, again, the reason I'm bringing this up is that you will see occasionally transition metal chemistry. It's often driven by changes in the oxidation states to them, sort of reaching what, again, we're not going to go into too much depth about. We're not going to get into why chromium might not want to be at 6 and would rather be at 4 and ultimately at even lower oxidation states, or why some metals would like to be at higher oxidation states than others. Those are things that you can learn in an inorganic class or an organometallic class. For the sake of organic chemistry, I'd like to try to keep things as analogous to, as I said earlier, substitution, elimination, and so forth. But we will see this, and so it's worth it to just sort of notice it, recognize that there are some differences between these from that standpoint. So does this make sense? To a certain extent, hopefully. I see you look like, oh, maybe. I said, does this make sense? And then I saw you go.
Oh, I was wondering, if there are carbons after the double bond?
So this right here?
No, the second one.
This right here. Yes, that is the aldehyde that we've made through the elimination. So it's in essence like an elimination mechanism. Okay? All right, so, and again, this is, if you read the book, this won't be the end game. It goes a little bit further than that. That's going to break down. But again, I just sort of want to focus on, I think, the important point here that you're, in this example, what you're doing is you're going from 6 bonds to that metal, to 4 bonds, that in essence takes it from what would be considered a 6, an oxidation state of 6 to an oxidation state of 4, which you can learn more about in inorganic or nanometallic courses. Yes?
You always want us to show the oxidation state.
I think it's worth it to keep track of it. Yes. Now, the challenge there, and this is why I'm not going to, I think it's worth it to start counting. I've gone back and forth on how much emphasis I've wanted to put onto these because it is such a different mechanism. I think that because of that, it can often confuse you guys. Because a perfect example would be like, I showed osmium tetroxide previously, and we think about like carbon. What would be an analogous thing of a carbon in that case? And it might be a carbene, and so, which I guess you could consider carbene as a different oxidation state, certainly, right? It would be sort of like a, it's got 6 electrons rather than the 8 that it would normally have. But again, I think that it is, we don't see this too much. But we do see it enough that it's at least worth going over once, sort of recognizing that there is this oxidation state, and that's often what drives this reaction, is that certain metals prefer to be at a specific oxidation state. And so if you're not at that oxidation state, if you're lower than that or if you're higher than that, then you may drive oxidation or reduction chemistry by mechanisms which involve the metals trying to get to those to change those oxidation states. So you'll see it a little bit. So, but again, try to draw as much of a parallel as you can in those 2 mechanisms that you've seen in the past. So we showed one example here, which in many ways this mechanism, if you sort of completed this in terms of the way that I was thinking about losing water, this would be very analogous to what you guys are going to see of an esterification reaction. So you'll see ester formation between a carboxylic acid and an alcohol, and you could draw a mechanism that would be very, very parallel here. Then this mechanism becomes very much like the elimination that you've seen. What differentiates them is, and what takes them to a different complicated nature, is the considerations for the oxidations of the metal. One question, then another one. So go ahead. So this is to an aldehyde, yes, that's a great question. So I just showed the one that is perfect. Yes, I can go to completion here. So chromic acid, if this were PCC, we would be absent from any water in this reaction. Thus, it would stop at this stage. But generally, and specifically with chromic acid, it is in water. And so, again, I don't want to go, but thank you, because I'm glad, because I could see that this would then lead to confusion to say, oh, chromic acid leads to aldehydes. No, I was just trying to go through one cycle of the mechanism. The complete mechanism, right, would recognize that this is actually conducted in water, right? And again, this gets to carbonyl chemistry, which we're not quite at yet, which is oftentimes why I like to teach a lot of oxidation and reduction chemistry after we learn a bit about carbonyl chemistry, because again, here's a mechanism which you'll see will be analogous to carbonyl chemistry. And what we'll see about carbonyls is that, let me just balance this equation here, is that carbonyls will often exist in the presence of water as hydrates. I'm getting a little bit nervous that I'm getting a little bit too far ahead of myself here. So we'll come back to the mechanism of how the hydrate forms, and we'll talk about this a little bit more. But what happens is, so once we get to carbonyl, we'll go through the mechanism of how this happens. But what I'll just tell you right now is that aldehydes, it's a very, very slight equilibrium towards the hydrate. But Le Chatelier's principle basically says that as we consume that hydrate, right, and we drive it towards the product, then eventually we can siphon all of the aldehyde throughout the whole reaction. So it is a mild equilibrium in most cases. There are special cases where if you have, say, for example, a trichloromethyl group here, that will actually favor the hydrate. But in 99% of cases, I just made that number up, I don't know, but in the majority of cases, you will see the hydrate as being an unstable intermediate. But then what you would do is you'd simply go through the mechanism from the hydrate, and as you sort of carry it through that mechanism, you'll basically see that then during the step, you'll have a hydrate here, right? And then when you do that elimination, in essence, you are now generating carboxylic acid. Does that make sense? Okay, so again, the difference between PCC at its core is that you can run it without any water around, so you don't generate that at all. Chromic acid is run on water, so it does allow this equilibrium, which does lead to the oxidation. So, hang it over here.
What was that? The purpose of that first arrow where chromium has the 5 bonds, no right under? Right there, yeah.
Oh, yeah. Yeah. No, I screwed up this. Yeah, so this was not the intermediate. Thank you for the catch. So that should have been the intermediate. And this, sorry, I said let's get to this, and then we never got to that, so I apologize. What is the relationship between this molecule here and this molecule here? What is the relationship between this, let's get rid of these arrows, and this molecule here? Again, balance the equation. What's the difference between this and this? Or if you were paying attention 2 minutes ago, what's the difference between this and this? What's that? H2O. Right? This has 1, 2, 3, 4, 5 oxygens to it. This one has 1, 2, 3, 4 oxygens, so there's 1 oxygen missing. This has on the chromium 1, 2, 3 hydrogens. This one only has 1, so it's H2O is the difference. So the relationship between these two is the analogy to a hydrate. And so the mechanism, again, as we'll sort of get back to, is you'll probably get a proton transfer, you'll leave water, and you'll generate the double bond, which now I'm sort of realizing you guys haven't learned about carbonyl chemistry yet, and we haven't discussed reactivity of carbonyl, so thinking about reactivity on carbonyls becomes perhaps a little bit difficult. So hopefully, you know, I guess a lot of the mechanisms involved in this right away, especially that breaking of that chromium-oxygen double bond, begin to get into carbonyl chemistry. So I'm glad that you sort of, whoever it was that said attack the carbonyl, but perhaps a more direct way at this point would just be the loss of water. But I do think that it's I'm calling it carbonyl, but it's a chromium-oxygen double bond. But that's more likely what it is, and we'll learn about that in terms of carbonyl chemistry. So again, I'm starting to realize now that this sort of the discussion on this sort of double bond and bringing up the double bond here, we haven't necessarily quite gotten to yet, but we will. And so, yeah. So there's another hand up. Yeah.
So now that you corrected it and put the double
Yes.
bond there, wouldn't the easier way would have been just the 2 electrons back one of the OHs?
Well, that's what we were saying earlier. So that was the initial question that was asked. So that everybody understands fully what we were saying previously. There's a more direct mechanism to get here, which is, I think, the question that's being asked, and which, based upon what you guys have learned to date, might make a lot more sense. And because of the fact that we haven't learned really about carbonyl chemistry yet, there are issues with this that should make you feel a little bit uncomfortable with drawing a mechanism like this. I think it's difficult to sort of, it's a dynamic system, so it's a little bit difficult, but you're under an acidic solution and you're losing, sort of OH minus, which isn't really something that you would want to do. The more likelihood is that if you were going to protonate, for example, this species, you'd probably more likely protonate this oxygen as well. So again, but we haven't gotten to carbonyl, so we're actually, from a mechanistic standpoint, worrying and nitpicking about the details of the mechanism at this point are probably not in our best interest. So if this is comfortable for you at this time, I would say okay, but have it leave maybe as water instead. Have it protonate H2O and then have it leave in that case. And remember that we are on sulfuric acid. And I don't love that either, but at least we're not generating OH minus in a solution. So if that's comfortable for you from a mechanistic
No, I
standpoint,
meant
that's fine.
generate an O minus.
So you don't want to leave O minus.
No, not leave. I mean, where the R is connected to the OH.
We're under an acidic environment. You're not going to deprotonate that, right? So, but let me ask you guys a question, because I think that I have some synthesis problems up here, but I want to take an opportunity right now to, I think, maybe build upon some of the questions here, because there was a little bit of confusion in terms of I misdrew this, so I apologize. Hopefully we corrected it. But let's try to correct this in a slightly different fashion as well. You know, no, I'm getting way into carbonyl chemistry. So are you comfortable with that? So in general, when you guys are doing mechanisms, let me just sort of state this, because this sort of gets to the core of why some of those suggestions were and why there's really no easy way to do this without perhaps invoking the sulfuric acid protonating the system to begin with. Anytime that you're doing a mechanism, there will be times, certainly there will be times when you're doing mechanisms where you will begin to have a positive charge on one part of the molecule and a negative charge on another part of the molecule. In the carbonyl, again, going back to the carbonyl chemistry, we will learn about avidic olefинation, where there really is no other way to draw this mechanism than to start separating some of these charges. In general, though, when we're thinking about mechanisms, really one of the things that you should try to do, and again, maybe we'll do that on some other problems that aren't complicated by the chromium being involved. But you generally want to either generate a negative charge and then start to shuffle that negative charge throughout the system, right? Or conversely, generate a positive charge and then start to shuffle that positive charge throughout the system. So it's the charge, whether it being enhancing the electrophilicity or conversely nucleophilicity to the system, which then sets off and sets everything in motion. So for those reasons, you necessarily wouldn't want to generate an O minus here. But on a sort of a chromium-mediated reaction, I think, you know, and we could have done it. We could have, say, for example, here, maybe the first step would have been protonate that. But I'm realizing as we're going through it, there's issues involving carbonyl chemistry that complicate it further. So I think protonating this and leaving as water, I'm perfectly happy with. And in fact, another way that you could sort of do this that would then you'd start to see parallels, for example, once we start getting to aromatic substitution chemistry, is let's say, for example, that we did. So one of the ways that you could perhaps think about this, and this will, actually I like this probably the best, what I'm about to say, which I think helps solve everything that we've been dealing with, and which then will reinforce what we're going to learn in electrophilic aromatic substitution chemistry. When you have this molecule that we've seen here, and we treat this, and we're in a solution of sulfuric acid, again, there's a sort of a dynamic system at play. There's an equilibrium. Everything is reversible, as we discussed last week. But if you were to protonate, you could protonate here. So kinetically, you might protonate here. You then might protonate here. The proton could certainly jump back and forth, depending on which one of those it would want to react with. But if you were to protonate here and generate that, the other thing about this is you could imagine very quickly leaving which again, it's going to be reversible, which then you could even imagine that being your electrophilic species. So again, we're getting a little bit more complex, but I kind of like this a lot too, as an intermediate. But again, it's all reversible, and you're in an aqueous solution, so maybe that would make it favor the other direction. But again, I'm making this way more complicated than it needs to at this point, and I think that there's some other questions. So let's move away from chromium chemistry, because the whole point of this was simply to try to relate it to chemistry that you guys have already seen. Unfortunately, what I'm finding is that because so much of this is analogous to carbonyl chemistry, which we haven't quite seen yet, it makes these comparisons a little bit difficult. I saw another hand up, or maybe it was your hand. Any other? Okay, so again, sort of following up on what we discussed last week, substitution, elimination, acid base. Again, no radicals to a certain extent. There's not too much in terms of radicals that we're going to be discussing, but you should certainly be comfortable with pushing radical arrows. Chromium, again, try to draw parallels as much as you can, but just recognize this oxidation change component which changes it. And again, you don't have to worry about why certain metals would want to be more stable than others. That's for a different course. But the last thing that we're going to get to, and that I got some questions today on is, and you started to do this last semester, it's, you learn about drawing molecules, you learn about redrawing molecules. You learn about reactions, you begin to learn about mechanisms of reactions, and then what you begin to do is you begin to tie these reactions together in synthesis problems. And so somebody came to me right now and asked me to go over a couple synthesis problems. So we can open the floor up for synthesis, or if somebody else has a mechanism problem, I think at this point a mechanism problem would trump a synthesis problem, but if you guys don't have any specific mechanism problems that you would like me to go over, I'll maybe answer these questions here. Okay. So, all right, so let's go to a synthesis problem. Okay, so, and you can't do synthesis problems without knowing all the reactions, so make sure that you know the vast majority of reactions before attempting too many synthesis problems. Oops. But I want to make one point about synthesis problems. So let's just move from left to right. So this question states that what we want to do is we want to start with butene, okay, and we're going to convert okay, and so this is going to certainly involve some chemistry that you learned last semester. I mean, right away, what you notice, right, is, you might notice a couple things just looking at this problem straight off the bat. I mean, the only real functional group that we have on the starting material is an alkene, right? And so one of the first things that you're going to want to make sure that you can do is know what the arsenal of reactions on alkenes would be that you might want to sort of use. It's also worthwhile to note that oftentimes how you draw the molecule can influence what you think about the synthesis. And so we've drawn it here in this specific way, but sometimes looking at it slightly differently can sort of help you see maybe alternative answers to the problem. This is, I think, one of the really important things about synthesis, and again, it comes back to one of these really important reasons why you guys are good at being able to redraw molecules and do so efficiently without making mistakes. And so if we were to look at this problem right off the bat, one of the things that we might do just intuitively is begin to already assign bonds from the starting material, for example, to the product, right? And so what I mean by that is, if we assign those carbons in this sort of fashion, we might be inclined to think that the 3,4 bond, right, of this alkene would ultimately become the 3,4 bond that I sort of outlined there. So the 3 would ultimately become a carbonyl, and the 4 would ultimately be that external bond. And the reason why this is important is that you might be tempted right away to try to get the right oxidation state at that center. I mean, this might be a way to go about it, but it's worth sort of noticing that you could also just redraw this molecule the other way. And again, that would open up an additional, maybe, vantage point that might suggest a different series of reactions to get to the products. And so the alternative way that we could draw it is simply just reverse what we have. So 1, 2, 3, 4, 5, 6. But now in this case, we've got 1, 2, 3, 4, 5, 6. And now we're coming from the outside, so we're at this carbonyl. Okay. Right? And so the alternative would be that 4, for example, could be where ultimately that oxidation comes up. So again, I think for the sake of this problem, I think the point that we want to sort of bring up here is not only are there different pathways through which we can go with them, but there's different ways in which we can view the molecules even, which will lead to an entirely different set of reactions to get there. So what I'd like to do is start to think about how we might want to perform this synthesis. And one of the ways that we might be able to do it right now, while maybe refreshing on some of the reactions, is just start to ask, what are some of the transformations that we know that we can do with alkenes, right? And this sometimes can be a nice little experiment when you're getting started to sort of maybe get your mind working, get it sort of moving in the right direction. But again, what types of chemistry could we do on this? And then from a single step, what might be some of the products that we might be able to form from this alkene? And we can go back and we discuss retrosynthesis in a minute, but sometimes I find this a helpful mental way to go about synthesis, at least at the beginning, to sort of view the different things. And in this case, I think it's worthwhile because next week you're going to be having questions on alkenes, and so let's revisit some of the alkene chemistry now. So what can we do to that alkene? Yeah.
You can turn it into a dihaloalkane.
So we can turn it into a dihaloalkane. Okay, so give me more specifics. So which one?
BR2.
So if we treat this molecule with Br2, that's going to react bromine across that double bond. Now, let's refresh on bromine really quickly. What do we know about stereochemistry of bromine? It's anti. Is it relevant here? No, right? Because there's two protons here, so recognize that it is a stereospecific process. I'm not showing any stereochemistry because there is really no. There's stereochemistry here, but again, this is not. We're not doing asymmetric catalysis here. We got to racemate, so we've got the mixture of enantiomer step position. So that's certainly one reaction that we can do on alkenes. What's another reaction? So acid catalyzed hydration. So that would be if we took this with some, say, sulfuric acid and water, or something of that nature. So we'll just say H plus H2O. And what would happen under acid catalyzed hydration? Right, so we add water across that bond. Now in this case, in bromine, it was Br2, so regioselectivity, it didn't really matter because bromine was ending up on both. Acid catalyzed hydrolysis, there is regioselectivity, right? So, and as sort of mentioned, it's Markovnikov, which can be explained mechanistically based upon the mechanism, right? So if you think through the mechanism of this, what's going to happen, you're going to protonate that alkene, right? When you protonate that alkene, you can put it there or there. It's going to go this way because the carbocation is what? More stable as a secondary rather than a primary, right? So then the water will add there. That's right. Make sure you know that. This gets back to yesterday. All right, so we can add the water across that double bond. This begins to kind of maybe look nice, right? Because we have an oxygen there, but it could also, oftentimes these sorts of things can also be sort of, red herring's the right word or not, but it could lead you down the wrong pathway. But it's worth mentioning, and it's certainly worth noticing that you do have an oxygen where you would ultimately like it, whether or not that's going to be useful or lead you down a path that's difficult. So yeah.
What about hydroboration?
So hydroboration is another option, and what's hydroboration?
So that is where you have an OH and ER, so it's kind of like a supposed to be.
Wait. Hydro.
So these
Oh, not hydroboration.
you like
Hydrolytic bromination. So you want to add bromine and water.
Yeah.
Oh, I thought, okay. So that would be called, so bromine in water. That's, it's like hydrolytic bromination, whatever you call it. So, so this would be the sort of the mixture in a way of these, right? We'd have water on one side and bromine on the other. Now, this is also asymmetric, if you will, right? There's going to be a bromine on one side and a water on the other. How do we rationalize the regiochemistry of this? So what's the regiochemistry of this reaction? Where should the bromine go? So I've heard two answers. I've heard more substituted, I've heard less substituted. So if there's confusion, let's think about the mechanism. What's the electrophile in this case? Bromine, right? Bromine's going to make the bromonium ion, right? The greater delta positive, ultimately where the water can attack, is going to be the one that bears the greater positive charge, right? So you can think about the resonance form of this, where instead of the bromonium, we could just put a full-blown positive charge on that. That would represent the resonance form that perhaps more generally reflects the charge distribution of this. And so this is the better, carries a higher positive charge. This ultimately is where the water adds in. Now, I like that one a lot. In a way, because why? What is, I mean, that's, yeah, because this is a really good one, right? Because you've done two things, right? You've put the oxygen, where at least as it is drawn here, where that oxygen will want to go, and we know how to get that oxygen up to the carbonyl. How do we do that? Oxidation, like we were just discussing, right? PCC, Jones reagent, one of those things, right? And we've got an electrophile here, right? And so all that we would in essence need to do is figure out a way to have a nucleophile that carries the two carbons. So we need to use some type of nucleophile that could react with that bromide and add the additional two carbons. So this looks like it could be a winner. Right, just sort of looking at it, and we can move forward with that one. Are there any other reactions? Yeah.
We could add HBr and peroxides to get it all alkane.
We could. So we could do. So there's the two HBRs, right? So HBr. So it was brought up HBr and peroxides. But HBr, we can certainly add HBr across an alkene. Let's just skip the peroxides for a second and come back to the peroxides and the significance of that. If we just do HBr, we get that. Sorry, no, I see my daughter in the back making noise, distracting me. So you get the bromine. Keep it down loose. But so the bromine here is going to go right on the more substituted alkene for the same reasons that water adds in that way. But if we were to add peroxides, right, what would happen is we sort of get the opposite, right? So it's sort of driven more by radical chemistry, HBr in the presence of a peroxide. Right, and so this is just a good little, this was nice to do. We don't need to go into this much depth in it, but I thought this was a nice just refresher on some alkene chemistry. Certainly there's other stuff that we could do as well. I mean, this is a nice winner, but let's discuss something else. I mean, there's another reaction that we haven't discussed yet that has a lot of the same benefits that I think this one brings up. But I think it's going to avoid some problems down the road, and I saw some hands shoot up. Oh, we didn't learn this yet. See, this is why I always get confused. You guys didn't learn about epoxides yet, did you? Did you? You didn't learn about reactivity of epoxides. You probably learned about the synthesis of epoxides, but you didn't learn about reactivity of epoxides. Epoxides is ultimately going to be the big winner here, and I think it's going to be the most efficient way to do so. But we'll come back to that in a second. You guys haven't learned reactivity.
But not the process.
Oh, so invert what I just said. Okay, so one of the ways that you make epoxides is through a reagent called MCBDA, which I guess we'll learn probably next week. But what is the nice thing about if I were to tell you that? right? An epoxide, you can do that with MCPBA, as we'll learn next week. And the nice thing about that epoxide is we don't have a lot of the same problems that we might have here. I mean, this is nice because it's got the electrophile and it has this at the right oxidation state. But the problem with this is that what were we saying yesterday about the challenge sometimes of alcohols? The alcohols can lead to problems. If you wanted to treat this with a nucleophile, you can do so, but what's the first thing that's going to happen? Like, say, for example, an alkyne, like a CH, like an acetylene, acetylide nucleophile. What's going to be the first thing that's going to happen? It's going to deprotonate this, right? So what's going to happen if we go through this route is we're going to have to protect that, then add the nucleophile, then deprotect it. If we go from the epoxide, we don't have to worry about that because we can add directly to that position. But anyway, so this was a good just practice in sort of knowing some of the different chemistry. We'll learn about this. But here's just some of the different things. Again, we can add bromine to the different positions. That's okay. And I think just looking at these straight off the bat, I think that this one just screams as being perhaps the most valuable and versatile compound. And then I'm going to come back to this one, hopefully on time, yeah.
Well, once we open up the epoxide and get the alcohol, how would we put a double bond on it?
How would we take an alcohol to a double bond?
But like, and make it regioselective to be next to the alcohol.
Wait.
To get the,
How would you add here and not here?
no, I guess what I mean is like, if once you open the epoxide and you need the tautomerism to get to that step.
No, it's not a tautomerism.
Oh.
That's an oxidation. That's simply alcohol. That becomes an alcohol.
But then-
Okay, let's go through it. Let's go through it because so the winner here, and we'll get back to the epoxide in a second. But I would like to get to see this. I keep getting back to this. I mean, the trick of doing synthesis so early in organic chemistry is that so many of the really good reactions you haven't learned yet. So we're going to learn, I think the way, so again, epoxide reactivity. Epoxide is probably one of the best ways to make it, but you guys don't have that yet. So let's just discuss what we just talked about. So we got bromine, water. We'll come back to the epoxide in a second. Okay, so we know that we have our electrophile here. We have our OH here. If, as I said earlier, if we want to treat this to a nucleophile, what are some of the good 2-carbon-bearing nucleophiles that we might want to use here? What's a nucleophile of carbon that we can add? Ethyl Grignards. Have you guys learned Grignards yet? No. Yes? You've learned Grignards. Grignards aren't the best things to do on alkyl halides because they'll often do eliminations. Did you guys learn Gilman yet? Right? So Gilman reagent, for example, is a good one. And usually you would probably want to go through the Gilman. So you can make that perhaps most directly through the cuprate. Right? So certainly if you've learned it's been a while since I thought about Gilman, but it's like this, right? It's QLE. So I believe it's this. I have to refresh. It's like that, I think, right? I think that. Is that Gilman? Yes. So it's a cuprate-based compound where you basically take methyl, or you take in this case ethyl lithium, you treat it to copper lithium, and you end up getting this. Okay, so that is a really good way to make that carbon-carbon bond. The problem is with this reaction is what's going to happen, even though this is a really good nucleophile, a lot of times these metal-based anions will also serve as bases. And so that's going to get deprotonated very, very quickly. So what's going to need to happen here is we're going to need to protect this. And the protection group that you guys learned and we discussed briefly yesterday was what? TBS, or one of these trialkyl silos. You said TES? So TES is another one. So these TRS, you can even say R being various, right? So TBS, TES, some we'll say test because that's what I heard, which is just tetraethyl silyl chloride. Right? Okay, that's going to protect it. So now if we were now to treat this with Gilman, so again, this is where you got to be really careful because you're building carbons here. So I would all urge you guys to really pay very close attention here because this is where mistakes can be made when we start growing alkyl chains. 1, 2, 3, 4, and you can even number them if need be. So 4 is going to be where the electrophile is. Right? 4. The bond is going to be effectively these electrons. Right? Are going to displace that bromide. That's going to be this bond. Right? And then you have 1 carbon, 2 carbons. And so you can double check your answer. Right, just by looking at counting the carbons, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and see that we do indeed have it right. How do you remove a test group? Who told me how to put one on? Bright Night, 2006. Can anybody help them out? How do we remove a silyl protecting group? Put on a silyl group with, yeah?
You add acids.
So certainly strong enough acids will remove it. So very, very strong acid is one way. There's another way, so I'm not going to write that down, so but yes. But it has to be fairly strong for it to be removed. But there's another way that we can remove it that's a little bit more mild and is a little bit more sort of orthogonal, so it's not going to do too many things with other groups. Anybody? Somebody? Fluorides? So you use fluorides. So sometimes HF, but HF is bad stuff, so it's usually things like tetrabutyl ammonium fluoride. It's usually something that's added. It's an organic soluble fluoride source. It's often referred to as TBAF. But really, it's about having the F minus, okay? And that's going to, the reason behind this is that, and I'll ultimately protonate that at the end, but the reason behind this is that a fluorine-silicon bond is extremely, extremely strong. So when people use an example of that sort of illustrates how strong this is you'll often see fluoride used with special glassware, because if you use fluoride with normal glass that's not coated with some special polymer, it will actually start etching the glassware severely. So you generally want to use specialized glassware. And then how do we get from here to here? Jones reagent, PCC, one of these oxidations. Okay. So back to the epoxide question. So the epoxide, which you guys haven't learned how to make, but you will learn next week, or unless you've read ahead. The epoxide the benefit of the epoxide is you don't have to worry about protecting the alcohol. Epoxides are electrophiles, right? And what did you guys learn about the reactivity of epoxides? So we can go after one carbon or the other depending upon the conditions that we use, right? You guys learned about this? So the one that's more substituted, well, you can go one way or another depending upon the type of reaction that you use. So the one case, it's more substituted, so what's going to drive that?
And it only worked with not.
You only did it with non-substituted?
No, I did it only not.
Well, so this is what I'm saying. So there's two arguments, and it's going to depend upon the conditions that you use. Yeah.
I would say so maybe it's a negative charge that would turn more positive on.
Well, so you're starting to get there. You're starting to get there a little bit. So what would be beneficial about going after this carbon? Just thinking broadly. Yeah. Speak up, I can't. So I'm saying you can do either. I'm telling you that is the truth. You can go either. What I'm asking you is to try to explain chemically, just more generally, what's an advantage of attacking this carbon? Sterics. What's an advantage of attacking this carbon? Better positive charge character. Okay? So it turns out that it's actually inverse of what somebody over here said. If you have a negatively charged species, you have a better nucleophile. You don't care as much about well, I mean, you do care about the electronics to a certain extent, but the overall species is neutral, and so it's more general that your nucleophile is going to, so if you have a strong nucleophile, especially a charged one, it's going to go the steric route. Okay? The way in which you go the electronic route is you have a weaker nucleophile, but you do it in such a way where you're actually activating. So this is sort of more negatively charged driven sequence. If you do this reaction in, say, for example, let's say we try to open it with, HBr or something like that, right? Let's say that we try to open this with HBr. We're going to protonate this, use Lewis acids and stuff. But you, in essence, instead of using a strong nucleophile, you activate through Lewis acid activation, or in this case, Bronsted acid activation of that carbonyl, making the overall system more positively charged. Now, which of those two carbons is going to bear a higher positive charge? This one. So whatever the nucleophile is in this case will now attack, and as I said, bromine, for example, will attack that way. So again, it's whether it's, you can go either way. It just depends upon whether you do it through sort of Lewis acid or Bronsted acid activation of the epoxides. If you make the epoxide a better electrophile, usually it goes towards the electronically better site. If you use a strong nucleophile, it goes towards the nucleophilic site. But both cases, after the quench, you're going to get to that same product. So it's not about a tautomerization at that point. It's just, so push the electrons, hopefully you'll be able to see that. Okay, so we're about out of time. But again, just a reminder for those of you that might have showed up late. There's a quiz next week. You're going to have 4 questions. 2 questions are going to involve chapters 6 through 9. 2 questions are going to involve chapter 10. You'll get a mechanism question for each chapter, and you'll get a what is the product of this reaction type 1. So know all the reactions, know the mechanisms of all of them, and you'll do great. So, thanks.